In the earliest days of the video game industry, nothing was more important to game development than efficiency. Games as software needed to be held in the smallest format possible and with the least computational complexity possible. As studios strove to meet the harsh hardware requirements of the time, several strategies were developed to handle graphics in the most efficient manners imaginable. For games like Atari's Battlezone and Lunar Lander, the solution was found in wireframe vector graphics, but for the vast majority of games from the industry's earliest era, the solution would take a different route. Pixel art. Pixel art is a technique of deliberately reducing resolution to an extremely low value, creating a stylized art form that has the twofold benefit of producing extraordinarily low spatial and computational complexity and being comparatively easy to create. Thus, the art style formed the backbone of game graphics for decades. In modern games, such strict requirements no longer shackle developers. The 2020 title Call of Duty Black Ops Cold War infamously had a console install size of 187.9 gigabytes, over 6.06 million times the 31 kilobyte file size of the original Super Mario Bros. From 1985. But, while vector graphics have fallen into obscurity, pixel art has not just remained, but it has thrived in recent years. Why? Well, beyond the nostalgia factor, unlike vector art, the secondary benefit of pixel art holds true to this day. Its barrier for entry is low enough that non-artist developers can make it themselves. One of the keys to pixel art's ease of implementation is a system called tile mapping, where small, self-repeating blocks of textures are arrayed, or mapped, to quickly create large texture fields. It's a fantastic system and has been used for decades with very little change. But it does have one notable downside. The human brain is remarkably capable of identifying patterns, and when applied to textures meant to be stochastic, it can easily cause a ghostly grid-like aliasing effect. This is particularly notable in natural textures and highly chaotic patterns. Up until now, this has been viewed as a necessary concession in exchange for the ease of implementation that pixel art provides. After all, almost no one has time to make an entire game's worth of unique pixel art. But what if you didn't have to? In 2001, Alexei A. Efros and William T. Freeman released a paper titled Image Quilting for Texture Synthesis and Transfer. It's a hallmark paper in the field of computational image manipulation and has been cited in thousands of later works. Image quilting works by taking many sample patches from an original image and generating an array of overlapping patches such that the overlapping regions have a minimal difference between their constituent layers. These overlapping patches are then stitched together with a minimum energy cut. The technique has been used to produce shockingly good artificially created photorealistic textures, but unlike the vast majority of previous research, which focuses on implementing image quilting to create lifelike results, this time we're going in the opposite direction. Our system of pixel art quilting is used to dynamically produce texture fields of arbitrary size for games, taking as input a single 64 by 64 tile, the same type that is used for a tile map, and creating non-patterned large-scale textures in as fast as real time. While conventionally, image quilting is performed on higher resolution inputs with a fixed output requirement, we look to operate on a live environment by making a few key changes. Firstly, by using a low input resolution, we can save a massive amount of computation time, immediately making a real-time solution more feasible. Secondly, we change the growth system to be able to function in an arbitrary direction of expansion. As the game moves right, the texture will expand right. As it moves down, the texture will expand downwards. To do this, we store an array of generated tiles by their world coordinates. Then load and stitch together the tiles currently in frame, adding to or removing from the loaded image as new rows or columns are brought into or leave the view space. When the system encounters a region that it does not contain data for, it selects a new set of basis textures for the unknown tiles in that region from the existing set of patches. Once generated, the tiles are hard saved to storage, meaning subsequent runs will perform significantly better in known regions and opening the door for effective regeneration. Finally, we alter the way that textures are generated and rendered, performing our iteration diagonally rather than line by line. This updated ordering allows the tiles in most direct proximity to the live location to be generated first, helping to prevent the player from being able to outrun the texture generation. To display the system in action, we have implemented a simplified demo in the Python game environment Pygame and set the same scene up in Unity using a tile map. As can be immediately seen, the pixel art quilted game has a far more natural look, with the repetition seen in the tile mapped game all but entirely absent. In a somewhat ironic twist, our system does fall short when used on the highly structured textures that tile maps work best with, as our sample patches are simply too small to reliably learn structural features. And even a single pixel of misplacement will be extremely visible in a structured pixel art use case. However, we believe that the benefits to stochastic texture generation are more than enough to stand on their own. While the current implementation still does have some performance and threading concerns, we believe that with refinement to the pre-generation and serialization systems, this could thoroughly be expanded into a viable product.